So what's going to be the next one?
The next one is pretty interesting. It's actually something new to me as well.
Is it? So I guess like we are curious to know what is it? Something new.
Well, we are going to learn about two things. One is ferrofluid, and the other one is superhydrophobic surfaces. Why do we now invite Benny Ng to let us know more about them? Dr. Ng, please.
Can you guys hear me? Yeah? Okay, so let's get started. So I have two topics to talk about today. The first one will be ferrofluid, and then the second one will be superhydrophobic surface. Okay, so now you get to see all the little pictures, and I try to explain what they are. So what is ferrofluid? In general, you can think about ferrofluid as a magnet, but in normal sense, not magnet is a solid, right? A piece of solid, but in this case, what we have is a liquid. Okay, something that kind of just like water, they move around, they're free fluid, but then they're magnetic. They have really interesting behavior. Okay, so that's a general definition. And more technical definition would be it's a colloidal liquid, and it's made of this really small magnetic nanoparticles. Okay, and I'll talk about what is nano and what will be magnetic nanoparticles. And then so magnetic ferrofluid was first developed by NASA. Okay, and it's back in 1960. And the reason they want to make about this ferrofluid is think about when you're in space, there's no more gravity. Okay, so how can we get the fuel to the engine to move the spaceship? Okay, that's the whole reason. We want to have another way to transfer fuel to push the rocket, right, or spaceship. So what's a nanometer? Nanometer is really, really small, as I said earlier. It's about 1/1000th of a meter. So what does that really mean, 1/1000th of a meter? Well, look at the little pictures. So we have 1 meter is about 1,000 millimeter. And now let's go to jump all the way to the small scale, right? As Dr. Leung said earlier, a human hair, the diameter, the thickness is about 50 microns, so about 50,000 nanometer. What about the size of the virus? The size of the virus, it can be ranged from 10 to about 100 nanometers. They're really small, and you cannot even see from your, light microscope, the one that you have at school, unless you have some really advanced, expensive piece of microscope. Then you can see that. The diameter of the DNA, the double strand, is 2.5 nanometer. So nanometer is really small. And for the magnetic nanoparticle that we have, they're talking about 10 nanometers in diameter. Okay, so they're really, really small, and you cannot see them with your light microscope because the light that we have, the wavelength, is about 400 nanometers. They're too big, right? 400 is big compared to 10 to 100 nanometers, so you cannot see them with your light microscope. And the magnetic nanoparticle basically is made of magnetite, Fe3O4, and hematite, Fe2O3. Okay, so those are the two components, there. Ferro means iron, so basically this is what it's made of. Ferrofluid will be made of magnetic nanoparticles. And they're so small, they don't even settle. They won't pull down by gravity, just like milk. If you lift milk, after a day or two, they still look like white in color, right? They don't just, all the fats components, they don't just separate into two different phases, right? Like sand and water, the sand will sink at the bottom, right? If you let it sit for a while, milk, it doesn't. Same thing for ferrofluid, they will not settle. Okay, because they're too small. Our room temperature, they're giving them energy to move them around. They keep bumping into each other by Brownian motion, just like they're drunk, they're like random walking. And so they'll never just stay or sink at the bottom at the end. Okay, so how can we keep all these tiny magnets from sticking to each other? Basically, well, we coat them with a surfactant. Think of surfactant as a material that's like a soap. Okay, and they have charges. In this case, we have some positive charges on the surface, on this little tiny magnet, so that positive charges and positive charges, they repel each other, so that they don't stick to each other. Okay, so that's one reason that we can make this ferrofluid from sticking to each other. Otherwise, all these little tiny magnets, they will stick together, and then they'll just sink at the bottom. Then it won't work. And as I showed you guys earlier in the first picture, you saw the ferrofluid, they have all this little spike. How do we generate those spikes? Basically, the spike you see is they're trying to visualize the magnetic field from a magnet. Every time they have a magnetic field, they will interact with it and they will form those spikes. And the stronger the magnetic field, then the more spikes they will have, and the higher the spike. So you can see from this picture, you can see that visualizing the way how the magnetic field is there. And the spike basically is trying to balance in different forces. Okay, in this case, we have the magnetic forces, you have the gravity and the surface tension. They try to all balancing all the forces together. So the magnetic field is going up, and the gravity and the surface tension try to pull it down. So you have this like competition. Okay, you're trying to balance a competition. And in nature, when you study chemistry, it's all about trying to minimize the energy. Just like if we can just play and not do any homework, that's what we want to do. Minimizing the amount of work that we have to do, or just say, keep the minimized energy. Hopefully you're still listening, not falling asleep. Haven't wished that minimum energy stay there. In terms of the application, Ferrofluid, well, it's just a way for me to play with, or for you guys to play with today. But the magnetic nanoparticle actually has lots of application. Nowadays, first of all, for the Ferrofluid, you can use it in loudspeaker. Not yet. That's coming. Okay, you can hear the loudspeaker. But usually we use it to cool down the coil in the speaker so that your speaker will not overheat and melt. Okay, so that's one way for Ferrofluid to use. And you can also use it to prevent all this like mechanic robot from wearing and tear. Okay, because they're just a fluid, they can have a really good seal. And in terms of the nanomedicine, that's another really hot topic. So if you're into like nanoscience, nanoengineering, in terms of the healthy aging, actually some people have already tried to use this really tiny magnetic nanoparticles in target drug delivery. For example, so I have this magnetic nanoparticles in here, and instead of coating it with the salt, the positive charges, I can actually coat it with maybe drug molecules. If you get sick, you get fever, I can put the drug molecules and on the magnetic nanoparticles, and then you take the medicine. Because they can interact with the magnetic field, you can have a really big magnet, and then you can direct toward where the drugs will be, and then you can do the delivery of the drugs. Okay, so that's one way. And another way, actually, people have been just start doing this therapy. It's for cancer treatment. I think this is in Germany. I think they just started like early this year. And I'm going to show you the video how they can use it for treating the cancer.
The centerpiece of the MagForce nano-cancer therapy is the nanoparticle, consisting of iron oxide. The particle is covered by a patented coating which ensures a good stability and division of the iron oxide particles in the tumor tissue. The small size of the particle is decisive for the therapy. The diameter measures some 20 nanometers and is thus 500 times smaller than a red blood cell. 1 milliliter of the particle solution contains nearly 17 trillion single nanoparticles. This high density makes efficient treatment possible. At the beginning of the therapy, the nanoparticles are injected directly into the tumor. The tumor in this particular case is a glioblastoma, a malignant brain tumor characterized by aggressively growing cells. On the microscopic level, the healthy cells can be seen on the left and the tumor cells on the right. After being injected, the nanoparticles spread out in the spaces between the tumor cells. The patient now enters the therapy device in which an alternating magnetic field is produced which is of no danger to humans. This field affects a 100,000 times alternation of the magnetic poles within the particles per second, creating warmth which is precisely regulated from outside. This application is repeated and the thermal effect increases visibly. The particles begin to oscillate, causing the cancer cells to die either from active self-destruction or from swelling until they literally burst. Tumor growth is stopped and the destroyed cells are discharged by the body in a natural process. As a rule, the 1-hour minimal invasive treatment is repeated 6 times. However, the particles are only injected once, thus making the therapy especially gentle on the patient.
So basically, you can inject the patient with magnetic nanoparticles, and then you just put in alternating magnetic field, and then the magnetic nanoparticle will heat up, and then once it heat up, it will just kill the cancer cell. So this is already in application right now. Okay. So Ferrofluid, inside this science application, what else can we do with Ferrofluid? Right? There's actually lots of application we can do in terms of art. Okay, for example, we can actually make some Ferrofluid structure. For example, by Sakiko Kodama. Basically, she started in 2007. She has a series of artwork based on Ferrofluid. Okay, so this is one picture of her artwork. Do you guys like basketball? I mean, if any of you guys like basketball, do you know Kevin Durant? His latest shoes, actually displaying in New York City at the Nike store, actually they play with Ferrofluid as well. Okay, so you can see the Ferrofluid moving along with all the magnetic field. So you can actually use it as a pop art. And you can also try to play with typography. You know, this is a smart program, right? You have science, mathematics, and arts, right? So we try linking the science and arts together. You can actually make different alphabet with Ferrofluid. Okay, so you need just to construct a magnetic field. Once you understand the science behind it, now the arts, the creativity is from you guys. You can even make a clock with Ferrofluid. You know, so this is, you can make a clock with Ferrofluid. Of course, that requires some engineering as well, but it's your imagination create all these different applications. You can also change how they look like by putting some watercolor. Okay, and you guys are going to play with that later this afternoon. And before I start, there's one more thing we can do. So I have a US $1 bill. I don't know if you guys haven't seen it before. How do you know they're real? You can choose some magnets, right? So I have a really strong magnet, and when they print the dollar bill, they have iron particles, you know, the one that I just talked about in lecture. So if I put a magnet close to it, let's see what will happen. They repel. And if I put the other side, let's see if I can keep it up. Can you guys see it? The dollar bill will just stick to the magnet. So this is another way. Not that many people know about these tricks, but you can test if they have any like magnetic ink in the dollar bill. You can try with your Hong Kong dollar bill. I don't think the $10 bill will work because they're plastic, but you can try either one. So moving on, so we finished the Ferrofluid part. Now let's go to the superhydrophobic surfaces. I think that will be the exciting part. Of course, there will be a demo at the end. I like this topic because actually I learned it from literature. Okay, I'm not sure if you guys have studied this article before. Basically, what it says is that I love only the lotus for growing the mud, but it's not stained. Hatched by clear waste, but it's not seduced. Okay, this is back in like almost 1,000 years ago. Okay, and why do I talk about literature? I mean, I thought this is events organized by the Faculty of Science. We're talking about science, mathematics, and arts. Maybe I should add another letter, L, right? Literature. Well, what I'm going to say is that actually Joe is the visionary nanotechnology scientist. Okay, it's really visionary in the sense that he actually observed the small changes in nature, and we cannot really explain it until 1,000 years later. And actually have many applications. Maybe some of you guys are already using them already. How do lotus leaves clean themselves? I mean, you look at the literature, they say, oh yeah, they grow in mud, they grow in the pond, they're dirty, but they're always clean. Okay, you can see they can easily pick up those dirt particles. Okay, how do they do that? Do you think they have a maid or cleaning lady and just every morning before you go there and try to like clean every single leaf? No. They have a really smart self-cleaning system. But before I talk about it, we need to understand what is surface reactivity. It's the ability for a liquid to stay on the solid surface. Okay, sometimes you add a drop of liquid water on some surfaces. They love the solid surfaces, so they spread out. They're really flat. But sometimes they don't like water, so they form a little water beads. Okay, so this one they're really wet, and this one has the least wet. Are we okay with this idea? If they beat up, they don't like water. If they love water, they flatten. Okay, let's keep this concept in mind. So now, because I have to introduce you the contact angle, a more scientific definition, you have to look at this angle. Okay, this is the surface, the solid surface, and the liquid. Okay, if it's less than 90 degrees, if this angle is less than 90 degrees, that means they love water, and we call it hydrophilic surface. So the surface really love water, so they will tend to be really flat. They will not form a little ball. Okay, if it's greater than 90 degrees, we will call that hydrophobic surface. Okay, so they tend to form a little bead, and they're easily to roll off. But okay, less than 90, greater than 90, that's easy. Well, now let's introduce, because my talk is about super hydrophobic surfaces. So what angle does it need to make it there? We need to be actually greater than 150 degrees, almost like this, in order to call it super hydrophobic surfaces. Since I think almost about 20 of you guys are going to play with this in this afternoon, and it's going to be fun. Now, I went to a pond, okay, I think last summer, okay, with my colleagues, and I saw water droplet, and then let's see what happened, okay. I try to mute the videos, there's no sound, okay, because otherwise, it's just fun. So, that was me holding the leaves, and I try to play with it. And toward the end, you hear someone screaming at the back. If I play you the music reader, do not play with the lotus leaf. That's why I use the music. Okay. And then so we add more water. You can see they just move along. They just happily move along. They just don't like water. So that's how they clean themselves. Okay. And this is called the lotus effect. So what at the beginning, when Zhao wrote the literature, what he did realize is that actually he discovered something really great. It's called the lotus effect. And we didn't even know it until maybe around 50 years ago, how to explain it. So that's why I think he's a visionary nanoscientist. Okay. What causes the water droplet to spread or build up? Basically, you can think in terms of the surface energy. Again, we always talk about energy, right? Energy and forces, we try to minimize it. We want to do the less amount of work. That's always the key for nature. It's spawning us. We're lazy, in general. We can't help it, okay? The whole idea for this is that if you look at this water, okay, they're surrounded by 6 other water molecules, everything is perfectly fine, so they're happy. Okay? But if you look at the water molecule on the top, on the surface, they're missing 2 water molecules to keep them happy. So they're not happy in here. So what happened is that while we were talking about the cohesion, okay, between each other, the interaction between each other versus the adhesion with the interface, with the air surface and the liquid surface. What happened is that when you have a bunch of unhappy water molecule at the surface, they still want to get closer to each other, so they curve up. Okay, so that's why you have this hydrophobic surface. So you're talking about the surface tension in here. Can we modify the surface to attract and repel water? Yes, we can actually do 2 items. Okay, surface chemistry and surface roughness. Those are the 2 things that we can do. I'm not going to go through the details about this bonding because Dr. Leung, he's going to talk about more in his workshop. And we can do some surface chemistry to change the surface to make it more hydrophilic and also hydrophobic. And in terms of the nano roughness, when you have a really smooth hydrophobic surface, you already form this contact angle greater than 90 degrees. You can actually make this really pillar, really small scale. When you add the water molecules, you can see the angle will be even greater. Because all this air, remember, they're hydrophobic. Air pockets are hydrophobic, and so if you add more and more of this, the water cannot go inside. And you have this hydrophobic superhydrophobic surfaces. Go back to here, the lotus leaf that we've seen earlier, right? So if you actually have this really, really powerful microscope that I talked about earlier, you look at the structure of the lotus leaf, what you see exactly like this. You have this like really small nanostructure. Okay, we're talking about 100 or 200 nanometers tall little poles, okay, to keep the water from going like sticking to the surface. And then if you zoom in this one of this little pole, you can see even more little like finger-like structure to try to really get rid of the water. And at the end, the water will just roll off. Well, besides the lotus leaf, what else can we do or we see from nature that have these similar properties? Well, pond skater, they stand on the surface, okay? They don't sink, they can just move quickly. And once you know this science idea, we can actually duplicate or replicate it. Okay, this is our own version of a pond skater, okay, using the idea of superhydrophobic surface. Butterfly. Have you ever wondered, how come the butterfly during the rainy day, they don't stick together in the wings? Because if you actually have a really powerful microscope to look at the scale of the butterfly, they have all this nanostructure. And then so the water will not stick on the wings, then they can keep flying. Otherwise, during the rainy day, maybe like today, you should see a lot of like butterflies just laying on the floor because they cannot just fly, right? Because the water, if they stick to the wings and then they're too heavy, you can just pick them up. You don't even need to catch them anymore. Okay. Shark. Actually, if you look at the quick close look at the shark, actually they also have all this nanostructure. That's why they can swim there. Okay, and we can duplicate this technology, mimic this technology by introducing this fast skin swimwear, so to help the swimmer to swim faster. Actually, more than 130 swim records have been broken from 2008 and to 2009. So in 1 year, more than 130 swim records have been broken. And then guess what happened at the end? They have to ban this technology because it's not fair. Or someone that have this really super duper, swimsuit, and the other people that just have regular swimsuit. Well, we can also do other things. Okay, let's watch a video because maybe you can come up with additional application.
One, two, three.
They don't like water. The first one was with treatment. Now they don't have it. They don't have treatment. They repel water. Oops. Can be your cell phone. So this may defeat the purpose of having a tissue paper. Because you actually want to soak up water. It's like cooking, you can actually play with it. Sunny side up, anyone? Have any school preference? think we can use this for cooking, right? Don't eat the bread, please. You know what I mean.
Oh my god.
The food guy work at the sandwich station, you know, so try to give me some like butter. Go back to the mud test.
1, 2, 3.
They put jaw, you know, who got the strong end of the strong, so they actually. Oh, I don't have time to show this. Actually, you can actually get this technology in Hong Kong. You know, it's called electropel. You know, for your cell phone, you want to be waterproof. You can also do that using this kind of technology. Today's workshop, in workshop 1B, what you try to make is something called the superhydrophobic surface. Your contact angle is going to be almost 180 degrees. Okay, and the roll-off angle for the water to roll off will be less than 1 degree. And let me give you a quick demonstration what we're going to do today. Okay. So I have two already treated surface, okay, and I have water, and I'm going to add some water. This is on flat surface, okay, so let's see what happens. Now you guys can see the water will just bounce off. They don't stick on the surface. But if you want to play with something else, you can actually get the Hong Kong U show up pretty nicely. But everything else, they will just bounce off. And if it's not clear, let's play with smart. Oops. They will just bounce off. They don't stick on the surface, except the letter that I have for you guys today. Okay, so that's smart, and that's Hong Kong U Smart Project. So hopefully, what you realize from my talk is that chemistry has become the center of science. Okay, oh, I need to switch back to the absolute PC. Okay. So hopefully what you discover is that chemistry has become the center of science and very interdisciplinary. Okay, and pay attention to your surroundings because you never know. One little observation that you have now, you may never know what will lead to a big discovery later on. It may take 1,000 years. Maybe you will not realize it, but it will be there. Okay, and live smart, guys. Okay, thank you.